welcome to lecture 6 CMOS RF integrated circuits. We were discussing matching networks. In particular, we had discussed the L match in quite detail, and then we decided that the L match might not be the end of the story, because there are only 2 degrees of freedom. So, this is what we had done in the previous lecture. We found that the L match uses 2 components, an inductor and a capacitor, and the ratio of the source to load resistance, that is the transformation ratio, that determines the Q of my network. Once the Q of my network is decided, the value of the inductor is decided. Once the value of the inductor is decided and at a given frequency, the value of the capacitor is also decided. So, we do not have any freedom to choose the Q given the transformation ratio that we desire, given the center frequency, everything else is frozen in the design. So, this was the drawback that we were working with in the previous class, and the solution was that we said that instead of having 2 components, let us go for 3 components. And we drew these 4 networks, we call them the pi match and the T match. So, these 4 networks presumably could solve my problem, and today my plan is to discuss both of these networks and more networks if necessary, and we will put a close to this entire topic. All right. So, the pi match, let us consider this first. I like this particular one because, so between this and this, I prefer this for reasons that you will find out soon. So, this is my plan, that I have got one inductor, 2 capacitors, and I want the total input impedance looking in from the other end to be equal to R s at omega naught for maximum power transfer, right. And I want a certain quality factor of the entire network. I do not want quality factor to be determined by the transformation ratio or anything else. Quality factor is a given, omega naught is a given, R s and R l are given, this ratio is also given, right. So, this is my situation. Now, how you can conceive of conceptualize this network is as follows. Let us split L into 2 pieces, L 1 and L 2. Now, at omega naught, I am going to plan to make the impedance looking in from in front of L 2, let us call this R intermediate. So, I plan to make this impedance looking in from in front of L 2 to be purely resistive at omega naught, and at omega naught I plan to make this impedance also look purely resistive. Okay. So, to do that, what you can think of is as follows. You have got a network that looks like this. So, C 2 in parallel with R L can be transformed to a series combination of C 2 and R L. So, what happens to C2? First of all, what happens to RL? Does the impedance of RL increase or decrease? Right, the impedance of RL decreases by the Q. What is the Q in this case? Q of this particular sub network, let us call it Q2, is equal to omega naught RL C2. Remember, larger the RL, larger the Q, because RL is in parallel with C. So, R comes in the numerator. So, this is my quality factor of the network. Now, RL is going to decrease because you are going from parallel to series. So, at omega naught, instead of RL, you are going to see RL divided by 1 plus Q2 square. What is going to happen to C2? C2 is also going to change. How is it going to change? Is it going to increase or decrease? When you go from parallel to series, the impedance is going to decrease. Am I right? So, Cs is going to be equal to Cp times 1 plus q squared by q squared. So, the impedance is going to decrease, means the capacitance is going to increase in the series case a little bit. Okay. And you choose L2 and C2 such that L2 and C2 resonate at the chosen frequency. So, omega 0 squared is equal to 1 by omega 0 squared is equal to L2 C2 times 1 plus Q2 squared by Q2 squared. So, this is one design equation. Okay. So, you keep this design equation in mind, and basically you choose C2 accordingly. You also have to keep this design equation in mind. All right. Now, next, what am I left with? I am left with a resistor. Suppose inductor and capacitor resonate with each other at omega naught, then the series combination of inductor capacitor becomes equal to 0 impedance, it becomes a short circuit. So, as a result I only see the resistance R L by 1 plus Q 2 squared. So, at omega naught what I see is as follows. This is what I see at the frequency omega naught. Now, we can further transform this. L1 is in series with a resistor. So, this can be transformed into a parallel combination of an inductor and a resistor, and what is going to happen? This is going to transform into capacitor in shunt with inductor, in shunt with a resistor, and the value of this resistor is going to be R L by 1 plus Q 2 squared times 1 plus Q 1 squared. Okay, the value of the resistance is going to increase when it goes from series to parallel. Yes. Okay. And what is going to happen to the value of the inductance? This is going to decrease No, this is also going to increase. Marginally. Right? What is the value of Q1 in this case? What is the value of Q1 in this case? Q1 is solely determined by the inductor and the resistor, right. You are transforming inductor in series with resistor to inductor in parallel with resistor. So, at omega 0, Q1 is going to be equal to, the smaller the resistance, more the Q. So, L is going to come in the numerator, resistance in the denominator. This is the Q1 that we are talking about. Fine. Okay. So, this is what we have got, and next step we have to make sure that the new inductor cancels out with the capacitor C1. So, we have to make sure that omega 0 squared is equal to L1 C1 1 plus Q1 squared by Q1 squared. Okay. So, once we make sure of this, L1 the inductor and the capacitor resonate out when they are in shunt with it is a shunt parallel resonant circuit. So, it is an infinite impedance. So, it is as good as it not being there. So, you see only the resistance, which is R L times 1 plus Q 1 squared divided by 1 plus Q 2 squared. So, this is the final resistance that you see, and you have to make R s equal to this quantity. Right. This is basically the idea. Now, in basically one step you are increasing I am sorry, you are decreasing the resistance, then you are again increasing the resistance. Yes. So, you have to choose your Q 1 and Q 2 in a fashion that it satisfies this. Suppose Q 1 and Q 2 are both large quantities. In that case, this basically simplifies to R s equal to R L times Q 1 squared by Q 2 squared. Okay. And also what else simplifies? These inductors and capacitors simplify considerably. Basically, the values of the inductors and capacitors are more or less the same. So, omega 0 squared equal to 1 by L 1 C 1, and that is equal to 1 by L 2 C 2. L 1 plus L 2 is the total inductance. Okay. What else is missing here? Q 2 is how much? And Q 1 is omega naught L 1 times 1 plus Q 2 squared by R L. Okay. Now, we have all of these equations, Now, what is missing? There is one big piece of information that is missing. The Q of the total circuit is missing. So, when we started off, we said that I know R s, I know R L, I know omega naught, these are all design parameters, and I want a certain Q. Why do I want a certain Q? Because I want a certain bandwidth, overall bandwidth of my matching circuit. So, I mean at a certain frequency it matches perfectly, and around that frequency over a little bandwidth it matches somewhat. So, I want to define what is the range of frequency over which it matches somewhat. So, the net characteristics is going to look like this. So, I want a definition of this. So, that is my bandwidth, that is the bandwidth of the matching circuit. It matches over that band approximately. It matches perfectly at only one point, but approximately over a range of frequencies. Okay, so, that is my overall Q. Okay. So, what is this quantity? If I have a circuit which has C 1, C 2 and L, what is the overall bandwidth of the match? Any thoughts? Okay, you can think of it this way. Let us try to work this out from first principles, right. This is an important idea. So, my input impedance Z in that is equal to a capacitor in parallel with some other stuff, right. So, that is what I am writing down over here. What is the other stuff? It is an inductor in series with some other stuff, and that is basically a resistor in parallel with a capacitor, right. So, the net quantity can be simplified to what? So, first of all let us try to simplify this lowermost quantity. This is yes, and actually it is never written in this fashion. It is usually simplified and written in this notation. So, at high frequencies the impedance is 0, at low frequencies I am sorry, at low frequencies the impedance seen is R L Does that pop out of this? Yeah, so I should not write it in this fashion. Yeah, so this is how we like to write it. So, at low frequencies the impedance is R L, and at high frequencies as omega tends to infinity, I have made further mistakes. Yeah, as omega, I have made mistakes here. So, please correct this, I am sorry. Okay, please make that correction. Okay, so we write this in this fashion, that is why it was not coming properly. Okay. So, these sanity checks always work, or always are needed when you do manipulations. Okay. And then let us try to simplify this entire term over here, and there you will basically get 1 plus j omega C 2 R L divided by R L minus omega squared L C 2 R L plus j omega L. Okay. So, the next step is to make the further simplification, and then we shall get R L minus omega squared L C 2 R L plus j omega L in the numerator, and in the denominator we are going to get 1 plus j omega C 2 R L plus j omega C 1 R L minus omega squared L C 1 minus j omega cubed L C 1 C 2 R L. So, this is my final expression. And this final expression at omega equal to omega 0, what is our plan? Our plan is that we have made this final expression in such a fashion that at omega equal to omega 0, this final expression is equal to R s. Okay. This is what you have done by your design strategy. Fine. Now, assuming that you have already achieved that, Let us look at a few issues over here. How are you going to compute the bandwidth? How are you going to compute the bandwidth? So, this can further be simplified, you are right, this can be further simplified into having a real part and an imaginary part. So, I can club real and imaginary parts in the following fashion. This will simplify a little bit. This will also simplify a little bit. Okay. So, I have clubbed real and imaginary parts together, and then what do? You multiply the numerator by the conjugate of the denominator, complex conjugate of the denominator, and then when the real part and the imaginary part are equal, that frequency is going to give you the 3 dB cutoff point. Agreed? So, let us take a step and do that. So, all right. So, this is what I have, and the real part has to be equal to the imaginary part, that will give me my 3 dB cutoff. So, let us do a little more work, and what I am going to get is as follows. Plus j times minus j is plus 1. So, this is the real part, and the imaginary part of the numerator is something of this fashion. And what we are saying is that when the real part is equal to the imaginary part, then at that particular omega, that is my 3 dB frequency. So, when these two quantities are equal, okay. First of all, what is the relationship between omega 0 squared and L and C 1 and omega 0, okay. We can't really say, right. This is what we know, and L 1 plus L 2 we know to be equal to L. So, we know this. So, it is almost like C1 in shunt in series with C2 has to resonate with L. Something like this. Of course, assuming that Q is large. Okay? Assuming that Q is large. Okay. So, what is this quantity in that case? You see why we did this, right? This quantity is approximately equal to 0 at the center frequency at omega naught. At omega naught, this quantity is approximately equal to 0. So, around omega naught, this entire quantity is going to be very, very small, right. So, this entire term is of no use to me. This entire term is also of no use to me. We like being engineers. So, we make a lot of these approximations. First of all, the big approximation here is that L1 does not really resonate with C1, L2 does not really resonate with C2. What resonates are a little different. These are actually my equations, but we assumed that Q is large. Okay. So, we made that engineering approximation first. Then the second engineering approximation that we are making over here is that around the center frequency, these quantities are still going to be very, very tiny. Okay. So, given that both this and this can be thrown out. Okay. Once you throw these two quantities out, you realize that the other two quantities have got to be more or less equal, which means once again we get some cancellation, which means that R L times 1 minus omega squared L C 2 has got to be approximately equal to omega L. Right. So, what does that mean? Can we find out omega? Does this remind you of something? Yes, it does remind us of something, that is the Q of the network. Okay. So, the way we compute the so this is what you are going to get. It does not matter, we just solve for this quadratic equation, find out the 2 omegas, and that is that. That is the end of the day, end of the story for us, right. And you can the way we solve for bandwidth is exactly the same, you end up with the exact same equations, and this is the Q in that case. Okay. So, this basically tells me that the net Q of my circuit this was my circuit that we started from. This basically tells me that the net Q is omega naught L by R L. It is almost as if I have a series combination of L and R, and C1, C2 etc. are accessories. Okay. So, that is the net Q of my circuit. Okay. Is there another way to see this happening? Well, another way to see this happening is to examine this from the center. So, we split it into two portions. So, the Q looking in to the right side is something, the Q looking into the left side is something. What is the Q looking into the left side? Okay. Now, you know what it is, right. Okay. So, Q looking into the right is something, Q looking to the left is something, and the total Q is the sum of these two Qs. So, that also gives you the same result, that Q is going to be almost equal to omega naught L by R L. Okay. So, what have we got so far? So far what we have got is a technique that is as follows. So, first we transform R L into some intermediate resistance looking in from here. This intermediate resistance is smaller or larger than R L? It is smaller than R L. Then we transform that intermediate resistance into a larger resistance looking in from here. So, we go down first and then we come up to the desired value. So, I needed a certain transformation ratio. Let us say I first go down by a factor of 1 plus q 2 squared, then I go up by a factor of 1 plus q 1 squared and reach my target. So, this is the strategy. Okay. The net q is the sum of q 1 and q 2. So, you have got a little bit of freedom over here. Q 1 can only be larger than q 1 and the total q can be larger than q 1 and q 2. So, suppose with an L match, this is what you were getting. This is my frequency axis, this is Z n. Okay. This is what you were getting with an L match. With a pi match, you can make the Q sharper. You can't make it broader, unfortunately. So, once omega 0 is decided, once R s and R L are decided, then the L match is fixed, whereas with the pi match you can tweak around a little bit, you can play around with L 1 and L 2 because you are going a step down and then coming a step up, right. So, you can play with the values of q 1 and q 2 and you can come up with a different value of the total Q. This different value is going to be larger than the earlier one. Agreed? Is this so far so good? Why is the different one going to be larger? Why not broad? Okay. It is like this, that for the L match case, R s by R L I am sorry, R L by R s is 1 plus Q square. Agreed? This is for the L match case. So, Q is something like this. Okay. In this case, what we are doing is we are going a step down first. So, we have two numbers Q 1 and Q 2. Q 1 is making the resistance smaller, Q 2 is going to make the resistance larger. The opposite actually, Q 2 is making the resistance smaller first and then you are going larger with Q 1. So, R L by R s is 1 plus Q 2 Q 1 squared by 1 plus Q 2 squared. Something of this fashion. So, looking at the two equations that you have got, R L by R s is the same. So, for the earlier one you need a certain Q. Here assume Q 1 and Q 2 are large. So, this is what you have got. So, the ratio, the square of the ratio of Q 1 and Q 2 is comparable to the earlier Q, which means that if Q 1 is something, then Q 2 has to be earlier Q times Q 1, okay, or vice versa. So, something like this. So, Q 1 squared has got to be Q 2 squared times Q L, and the net Q is Q 1 plus Q 2. So, it is definitely more than the Q of the L match, can't be less, right. So, you will get a much sharper match in this case. Fine, so far so good. Now, comes the question, why did I favor this particular network? The reason why I favored this network is because of parasitics. So, you might have heard of parasitic capacitances in earlier courses. So, whenever you have two objects, there is a parasitic capacitance between these two objects, or whenever you have one object, you have a parasitic capacitance between that one object and the reference potential, that is ground, right. So, these networks that I drew, let us consider this particular network. It is very hard to make this, because whenever I place L 2, there is automatically going to be a parasitic capacitance between the node the load and ground. There is automatically going to be another parasitic capacitance here. Whereas, in this case if I have these parasitic capacitances, they can be lumped inside the capacitors. So, C 1 and C 2 can absorb these parasitic capacitances, and once I figure out what these parasitic capacitances are going to be, I basically design in such a fashion that C 1 and C 2 are so much less. The desired total capacitance minus the parasitic, I design it in that fashion, right. So, that is why I kind of prefer this particular design as opposed to the next one. Next one is going to give you the identical, it is an identical situation with the next one. You now have to split C into two series capacitors. Each of these series capacitors are going to be smaller than the original, I am sorry, larger than the original one, right. Then there is the T match. What does the T match do? Well, the T match is which one will I favor? Will I favor this one, or is this going to be favored, or is this going to be favored? You are right, this is going to be favored more, because whenever I place that inductor over there, automatically there is going to be a parasitic capacitance to ground, which I will be very hard pressed to figure out what to do with it. Okay. Whereas, in this one, this parasitic is taken care of. There is also a parasitic capacitance here, which I have to worry about, and there is also a parasitic capacitance here, which is something I will have to worry about, but let us worry about these things later. Okay. So, let us look at this T match briefly. Okay. So, it is the same strategy as before. I split up this capacitor C into C 1 and C 2, they are in parallel. So, I split up C into C 1 and C 2, and now I have got L 2 in series with R L. I am going to transform L 2 in series with R L to an inductor in parallel with a resistor. Now, I am going up. Okay. Okay. And I make sure that C 2 resonates out with L 2 prime at the frequency omega 0. So, I can delete C 2 and L 2 prime both, and now from this point this is what I see, and now I have got a parallel combination of a capacitor and a resistor. This I will transform to a series combination of a capacitor and a resistor, which means that I will have to go down in terms of resistance. So, what is going to happen is something like this. Once again. So, once again very similar design equations, right, and you basically have to figure out the values of Q 1 and Q 2 such that you get the desired transformation ratio between R s and R L. Okay. If both Q 1 and Q 2 are large, then this certain approximations can be made, and L 1 and C 1 prime is little different from C 1. but as long as q is large, C 1 is almost equal to C 1 prime. Similarly, C 2 is almost going to be equal to C 2 prime. I am sorry, L 2 is going to be almost equal to L 2 prime, right. So, L 2 prime has to resonate with C 2, L 1 has to resonate with C 1 prime. All of these resonators have to resonate at omega naught, the chosen frequency of match. Once they resonate out, everything is clean and you just see the desired resistance. Now, the question mark here is, does this increase the Q or decrease the Q? This is something you need to find out as homework. All right. So, total Q. So, please do this as an exercise. Then there are a couple of other matching networks that are interesting. These are called tapped inductors or tapped capacitors. So, it is almost, it looks like a pie, right? It looks like this. You can redraw this in this fashion, but we call it tapped this is called a tapped capacitor match. And similarly, there is a tapped inductor match which looks like this. And which one is preferable? What do you think is preferable? Yeah, most probably the tapped capacitor is going to be preferable because it lumps into it the load parasitic capacitance. You are right. Okay. So, how do you conceive of this? How are you going to imagine this? So, the tapped capacitor match, you are going to split up C 1 into 2 series capacitors. Is that okay? No, it is not okay. What you have to do is think of the ratio C 1 by 1 plus C 1 by C 1 plus C 2. That is actually what is going to give you the transformation ratio. So, the older technique of splitting up the middle one into 2 pieces is not really going to work here. In any case, think of it in this fashion. You are going to transform C 2 in parallel with R L to a larger to a smaller series resistance and a capacitance at the frequency omega naught. And now you have C 1 in series with C 2 . C 1 in series with C 2 can be lumped together as one big capacitor, and now once again you can do the parallel series to parallel transformation. Where Q 1 is equal to Yes. So, the series combination of the two capacitors and the resistor, right, that Q you have to worry about. And this inductor and the capacitor need to resonate at the desired frequency. So, you have to put the inductor such that it resonates out with the value of the capacitor. Of course, you choose Q 1 and Q 2 accordingly. Okay. So, the question for you is, what is the total Q of this network? You have to figure out. This could be something that you need to do, you need to figure out by yourself. So, the total Q, once you figure it out, then you can figure out whether the Q is going to increase or decrease and how you can play with it. Okay. So, let us do a brief recap of what all we did. We basically started off with the pi match circuit, and we broke up the inductor into two pieces, L 1 and L 2. And first we were stepping down the resistance, then we were stepping up the resistance. So, the net transformation ratio was 1 plus Q 1 squared by 1 plus Q 2 squared. So, this was the net transformation ratio that I was going to work with, and as a result I found that the Q that I can get from this is much more than the ordinary Qs that I can get with the straightforward L match. So, this is the lesson learnt from this. Parallel exercises we can do with the T match, exact same methodology, and a different exercise could be the tapped capacitor or the tapped inductor matching networks. Okay. So, with this we are going to close this chapter, this entire module on RLC networks. So, under RLC networks we studied, basically we studied the parallel to series and series to parallel transformations, and then we studied a lot of different matching networks. Okay. So, thank you, and we are going to start a new module after this.